In this lecture, we will continue our studies on Lewis structures. We will examine the Lewis structure of methane CH4 in depth. After our examination of CH4, we will move on to other species. So let's start right in with methane CH4. We'll draw the carbon atom with its 4 valence electrons, and then we will attach a hydrogen, another hydrogen, another hydrogen, and another hydrogen. We make 4 bonds, and we have our Lewis structure for methane CH4. One of the things to remember on methane CH4 is that its electron geometry and its molecular geometry is tetrahedral. The molecule is very symmetric, and we will return to this property after we look at the electron configurations and orbital diagrams for methane. We consider the carbon atom in an unbonded state. Its electron configuration is 1s2, 2s2, 2p2. Let's draw an orbital diagram, but let's go ahead and indicate the relative energy levels of the orbitals in the carbon atom. We have the 1s orbital. Higher in energy, we have the 2s orbital. And even higher in energy, we have the 3 2p orbitals. It is important to remember that the further an electron is from the nucleus, the higher the energy of the electron. The closer the electron is to the nucleus, the lower in energy the electron. We look at the two 1s electrons in carbon, we realize that they sit right next to the nucleus. They are very low energy electrons. They are core electrons. We look at the electrons in the second shell and we say, well, we have 2s electrons and we have 2p electrons. Remember, the 2p electrons are further from the nucleus than the 2s electrons. They are at higher energy, and as we look at our orbital diagram, this matches. We say that the 1s electrons are lower in energy, the 2s electrons are a little higher in energy, and the 2p electrons are even higher in energy. We place our electrons first in the 1s orbital. Then we go higher in energy to the 2s orbital, and then we place our last 2 electrons in the 2p orbital. We look at this and say, well, now we have to place the electrons from the hydrogen atoms. So let's go ahead and do so, and I will indicate where the hydrogen atoms are as far as their bonding in an orbital. Remember, with our carbon atom, we shall say that it has its electrons, and we say, well, a hydrogen atom has an electron. And the carbon atom must accept the electrons from the hydrogen atoms. In other words, the carbon atom has its orbitals, and it will place the electrons from the hydrogen atom into its orbitals. So our carbon atom has 4 orbitals in its valence shell, and it will place the electrons from the hydrogen atoms into these orbitals. So we'll look at this and say, well, in each one of these bonds, we see 1 electron came from the carbon atom and 1 electron came from the hydrogen atom. And this matches what we know about covalent bonds. Covalent, a sharing of the valence electrons. So we'll come over here and I'll say, well, we're going to make a carbon-hydrogen bond, and I'll place the electron from a hydrogen atom into this orbital, and that indicates we have a bond. I'll come over here, I'll write another hydrogen atom, and hydrogen will donate 1 electron, and our carbon atom already has an electron. But if I come over here, I say, well, I can put an electron from hydrogen into this orbital, but there is no electron from the carbon atom. I could say, well, I'd like to form a bond here with this hydrogen atom, but this orbital is already full. So we'll have to readjust our orbital diagram to see if we can get it to match the actual bonding in a methane molecule. Again, we'll indicate the relative energy levels of the orbitals. This is the 1s orbital. Again, we have a 2s orbital. And again, we have our three 2p orbitals. We'll fill the 1s orbital knowing that these represent core electrons, and core electrons are unreactive, and thus we will not form any bonds with the hydrogen atom using this orbital. But I will place one electron in the 2s orbital, and then I'll place 3 electrons in the 2p orbitals. These electrons are carbon's electrons. So now I will place a hydrogen atom here, and I can form a carbon-hydrogen bond. I'll place another hydrogen atom here, making a carbon-hydrogen bond, another carbon-hydrogen bond, and our last carbon-hydrogen bond. So at first glance, it seems like we've solved the problem. We have 4 orbitals. Each orbital has 1 electron from carbon and 1 electron from hydrogen. This allows us to form 4 carbon-hydrogen bonds. But remember we said that the closer an electron is to the nucleus, the lower in energy. The further an electron is from the nucleus, the higher energy. As we look at the orbital diagram, it indicates that one of the hydrogen atoms is closer to the nucleus than the other 3. This is because the electrons in this carbon-hydrogen bond are closer to the nucleus of the carbon atom than the other 3. And yet, a molecule of methane is a very symmetrical molecule. All of the carbon-hydrogen bonds are equidistant. This must mean that we need to readjust our orbital diagram. The orbital diagram must indicate that all 4 carbon-hydrogen bonds are the same length. In other words, each hydrogen atom is the same distance from the carbon nucleus. We will draw an orbital diagram of an unbonded carbon atom. And again, we have the 1s orbital, the 2s orbital, and the 3 2p orbitals. And we shall say this is unbonded. What we mean by unbonded is that this carbon atom is not the carbon atom in our methane, CH4. We're just saying, well, this is the orbital diagram for a carbon atom when it is attached to nothing. And of course, we know that we have 1, 2, 3, 4, 5, 6. But we have to account for our perfect symmetry in our methane molecule. So now we shall make an orbital diagram in methane. We shall say that this is a bonded carbon atom. And again, we'll indicate the relative energy levels. We know that we will not adjust the energy level of the 1s orbital. The 1s orbital represents the core electrons, the unreactive electrons. We will, however, have to make 1, 2, 3, 4 orbitals that are of the same energy level. They have to be of the same energy level to account for the same distance for each carbon-hydrogen bond. So I shall raise the energy level of the 2s orbital, and I shall lower the energy level of our 3 2p orbitals. This gives me 4 orbitals of the same energy level. When we have orbitals at the same energy level, these orbitals are called degenerate, meaning that they have the same energy. So I have 4 degenerate orbitals. To make these 4 orbitals, I used 1s orbital and I used 3 p orbitals. So there is a superscript of 1 for the s that is not written. So we call each of these orbitals an sp3 hybridized orbitals. We are taking the 2s orbital and the 3 2p orbitals, and we are combining them to make hybrid orbitals. However many unhybridized orbitals we start with, we must end up with an equal number of hybrid orbitals. Now I can turn around and place my 2 core electrons for the carbon atom. And then I will place 1, 2, 3, 4 electrons. Remember that the carbon atom has 6 protons and 6 electrons. Now I can bring in a hydrogen atom, and I'll place the hydrogen atom's electron in that orbital. I'll bring in the other hydrogen atom with its electron, the other hydrogen atom with its electron, and the 4th hydrogen atom with its electron. Now as we look at this orbital diagram, we see that we have 4 carbon-hydrogen bonds, and they are of the same energy level. One of the key takeaways on this is that we know that the carbon atom in methane has a tetrahedral geometry. Now, the tetrahedral geometry is its molecular geometry, or the shape that the 4 hydrogen atoms and the carbon atom make, but it is also its electron geometry. So if we look at the pairs of electrons around the carbon atom, we see that these electrons form a tetrahedral geometry. The takeaway on this is that the electron geometry directly corresponds to the hybridization of that atom. I'm going to say that again because it is a very important concept. The electron geometry corresponds to the hybridization of the atom. Let's work some examples and make a table at the same time to illustrate what is meant. On our table, we'll consider the examples. And one example we just looked at was methane, CH4. And we shall consider the electron geometry. And in methane, the electron geometry is tetrahedral. We just ascertained that the hybridization of the carbon in methane is sp3. Let's go ahead and draw the Lewis structure for CH2O formaldehyde, and then we'll analyze both the carbon atom and the oxygen atom in this molecule. We'll place the less electronegative carbon atom in the middle. We'll place the oxygen atom in such a fashion that one of its lone electrons is oriented towards an electron for carbon so that we can make a bond. We'll bring in our hydrogen atoms with their lone electron, and we'll make bonds. We do not want to leave unpaired electrons. We have an unpaired electron on a carbon atom that will be moved to another location on the carbon atom, and we have an unpaired electron on the oxygen that will be moved to another location on the oxygen. We can now create a double bond. VSEPR indicates that we should not have a 180-degree bond angle here while having 90-degree bond angles here. Indeed, these bond angles should be the same. So we will redraw our carbon atom, and we will make the bond angles for the carbon atom all 120 degrees. Following that same mantra, we should not have 180-degree bond angles on these lone pairs on the oxygen and 90-degree bond angles between the lone pairs and these bonding pairs. So we will also move the lone pairs in such a fashion that they are at 120 degrees. So let's draw an orbital diagram for this carbon atom. Certainly, we have the 1s orbital. But we look at this and say, well, how many hybrid orbitals do we need? We need 1, 2, but are both of these hybrid orbitals, or is only one of these a hybrid orbital? When we get to double or triple bonds, the thing to remember is in a double bond, only one of the bonds is a hybridized bond. When we get to triple bonds, only one of the bonds is a hybridized bond. So as we look at this double bond here, we are going to say, well, one of these is a hybridized bond and one of them is not. So we shall say that we have 1 hybrid orbital, 2 hybrid orbitals, and 3 hybrid orbitals. And the other orbital must be unhybridized. What shall we label these orbitals? So this is the orbital diagram we will use for our bonded carbon. Let's again consider the unbonded carbon. We know that we have a 1s orbital. We know that we have a 2s orbital. And we know that we have 3 2p orbitals. Well, what we'll do is we will raise the energy of the 2s orbital, as we see it's up a little higher from where it started, and lower the energy of 2p orbitals. So to make this orbital diagram, we used a single s orbital and we used 2p orbitals. We still have an unhybridized 2p orbital. So we would look at this and say, all right, let's go ahead and place in the electrons for carbon. We have 1 electron, 2 electron, 3, 4, 5, and 6 electrons. We will place an electron for this hydrogen in the first hybrid orbital, an electron for the second hydrogen atom in the second orbital. We will place an electron for the oxygen atom here and the other electron for the oxygen atom here. So we look here and we see one of our carbon-oxygen bonds is a hybridized bond and one of our carbon-oxygen bonds is an unhybridized bond. So we look at this and see, well, one of these bonds is hybridized and one of these bonds is unhybridized. So we would look at this carbon atom and we would say, well, the carbon atom is sp2 hybridized. And we ask ourselves, what kind of geometry is this? Well, this is a trigonal planar geometry. So we can come over here and we can say, well, we looked at H2O, and the electron geometry was trigonal planar, and its hybridization was sp2. What we note here is that if we have a tetrahedral electron geometry, the hybridization is sp3. If the hybridization is sp3, then the electron geometry is tetrahedral. If we have a trigonal planar geometry, then the hybridization is sp2, and if the hybridization is sp2, then the electron geometry is trigonal planar. As we look at the oxygen atom, we should ask, well, does it have a hybridization? Clearly it does. We know that one of these bonds is a hybridized bond, and indeed the oxygen atom is going to have a hybridized bond. we have a double bond between carbon and oxygen. One will be hybridized and one will not. The electrons go in hybrid orbitals. So as we look at this, we say, well, if the electron pairs, we have one pair and two pair, and each pair goes in a hybrid orbital, then we need 1, 2, 3 hybridized orbitals for the oxygen atom. So again, we could look at our oxygen atom and we could say, well, it has a 1s orbital, and now I know it will have 1, 2, 3 hybridized orbitals, and one of the orbitals on the oxygen atom will be unhybridized. So again, we would say that these 3 hybrid orbitals came from a 2s orbital and 2p orbitals. So these are sp2 hybrid orbitals, and this is an unhybridized 2p orbital. So oxygen has 8 protons and 8 electrons. We will place our electrons in our orbital diagram. 1, 2, 3, 4, 5, 6, 7, and 8. In this case, we can place the carbon atom here and make one bond that is a hybrid bond, and we'll place the carbon atom here and make another bond that is an unhybridized bond. So as we look at our oxygen atom, we see that one of the bonds is hybridized and one of the bonds is unhybridized. We have worked the Lewis structure for CO2. Let's go ahead and work the Lewis structure for CO2 with a more in-depth analysis. Again, we have our carbon atom with its 4 valence electrons. We place the oxygen atoms. We make bonds. We see an unpaired, an unpaired, an unpaired, and an unpaired. We move these to make double bonds as we have done before. The bonds around a carbon atom are at 180 degrees, and this is the optimal configuration based off of VSEPR. We see the lone pairs on the oxygen atoms should be at 120 degrees, so we make one adjustment to our Lewis structure that conforms to VSEPR. So as we look at our carbon atom, we see that there are 2 double bonds. Take the double bonds one at a time. So we look at one double bond and we see that one of the bonds will be hybridized, the other will not. We look at the other double bond and we realize one of the bonds will be hybridized and one will not. So our carbon atom will have 2 hybridized bonds and 2 unhybridized bonds. So we could look at this and say, all right, we'll draw our orbital diagram. We'll put our 1s orbital at the bottom of the energy level. We'll make one hybridized bond and another hybridized bond. That means that we have 2 bonds that are not hybridized. To make these 2 hybridized bonds, we used a 2s orbital and a 2p orbital. So we shall call each of these orbitals sp hybridized orbitals, and we have 2 2p orbitals that are unhybridized. We'll place an electron for the carbon here and another here, and then we have 1, 2, 3, 4 electrons from our carbon atom. We know that one of these bonds is unhybridized and one is hybridized. We shall indicate this oxygen atom has an electron in the hybridized orbital, and this oxygen has an electron in the unhybridized orbital. We shall say, well, here's another oxygen atom. It will place an electron in the hybridized orbital, and it will place its other electron in the unhybridized orbital. So as we look at this carbon atom, we see that the carbon atom must be sp hybridized. We look at the arrangement of the electrons. We see that the electrons are 180 degrees apart. This means that the electrons form a linear geometry. We can say, well, here's our carbon atom, and let's just look at the shape the electrons make. I can take a straight line and draw it through the electrons, and so the geometry of this is linear. So we go back to our table, and we say that we looked at CO2. Its electron geometry was linear, and its hybridization is sp. Let's go ahead and look at another example. Let's look at PCl5, or phosphorus pentachloride. Phosphorus is less electronegative than chlorine, so we will place our phosphorus atom on our paper. Phosphorus has 5 valence electrons, and we will place these in 4 even regions around a phosphorus atom. We will bring in a chlorine atom with 7 valence electrons. We will bring in another chlorine atom with its 7 valence electrons, another chlorine atom, and as we look at this, we realize, well, this is a lone pair of electrons, but I have nowhere else that I can attach my additional 2 chlorine atoms. It is preferable to make phosphorus-chlorine bonds. It's not preferable to make chlorine-chlorine bonds. In other words, we should not have a phosphorus attached to a chlorine attached to another chlorine. If we can attach the more electronegative chlorine to the less electronegative phosphorus, that is a preferable bond. We do not want to form 2 bonds to a chlorine atom unless we have to. Chlorine prefers to fill its valence shell, and thus chlorine prefers to form only 1 bond. So we will split this lone pair of electrons, making them individual electrons that we can now attach chlorine atoms to. So we shall make bonds, and we have PCl5. Now, there could be an argument, and hopefully you're looking at the phosphorus atom and you're saying, well, this phosphorus atom has 2, 4, 6, 8, 10 electrons around it. And our octet rule says that we should only have 8 electrons around a period 2 element. But that's the key. Phosphorus is not a period 2 element. So phosphorus may expand its valence shell. We can put more than 8 electrons around a phosphorus atom because it is not a period 2 element. The octet rule only holds as a hard and fast rule for period 2 elements. Period 3 elements may exceed an octet. We look at this and say, well, is this a good way to draw the PCl5? And the answer is, well, maybe we can have a little better 3-dimensional representation of PCl5 by drawing it as so. And I will shorten this bond to make the drawing a little more symmetric. In this electron geometry, and the molecular geometry in this case, is called trigonal bipyramidal. We can envision a pyramid. If we think of these chlorine atoms being attached in this fashion and say, well, that gives me a pyramid on a top. But then I could say, well, can we envision a pyramid on the bottom? And yes, we can. So we see that there's a pyramid on the top between these three equatorial and this axial chlorine, and there's a pyramid on the bottom from these three equatorial and this axial chlorine. So if we looked at this, we could say, well, here's our phosphorus atom, and the phosphorus atom has a trigonal bipyramid. Structure for its electron geometry. Now again, in this case, the molecular geometry matches, but what we're after for hybridization is we're after the electron geometry. Now, bear in mind, when we have looked at carbon, carbon is a period 2 element, and we say that, okay, well, we go sp, sp2, sp3. Could we have an sp4 hybridization? Hopefully you're looking at this and realizing, no, there is not going to be an sp4 hybridization. What this would mean is that we have 5 orbitals, 4 p orbitals and 1 s orbital. Let's look at our quantum number mnemonic. Any shell contains 1s and 3p orbitals. Looking at the second shell, we see it has 1s orbital and 3p orbitals, so an sp4 hybridization is not possible. It's important to remember here that phosphorus is a period 3 element. So let's look at an orbital diagram for phosphorus. We certainly will have the 1s orbital. Then we will have the 2s orbital. We will have our 2p orbitals. We will have our 3s orbital. We will have our 3p orbitals. And we will have our 3d orbitals. Since phosphorus is a period 3 element, when it forms these bonds, it is forming these bonds using its valence shell, which is the third shell. So the orbitals that are hybridizing are the orbitals from the third shell. We see that we need 1, 2, 3, 4, 5 hybrid orbitals. So we shall hybridize the 3s. We shall hybridize the 3p. This gets us 1, 2, 3, 4 orbitals, and we will hybridize one of the 3d orbitals. So the hybridization of this phosphorus atom will be sp3d. And it is important to remember that the s orbital that was hybridized is a 3s orbital. The 3p orbitals that were hybridized are 3p orbitals, and the d orbital that was hybridized is a 3d orbital. So we look at it and say, well, this electron geometry is a trigonal bipyramid, and this is an sp3d hybridized phosphorus atom. So we shall say we looked at PCl5 and that its electron geometry was trigonal bipyramid, and its hybridization was sp3d. The hybrid orbitals for the carbon atoms that we have looked at in these species came from the second shell. So the sp hybridization in CO2 means that the s orbital and a p orbital came from the second shell. The sp2 hybridized orbitals in CH2O came from the second shell. The sp3 hybrid orbitals in CH4 came from the second shell, whereas the s orbital, the 3p orbitals, and a d orbital in PCl5 came from the third shell. Let's look at another example. We shall consider SF6, sulfur hexafluoride. We'll draw our sulfur atom with its 6 valence electrons. We'll bring in our fluorine atoms. We'll make bonds. And we will follow the same mantra that we did with PCl5. We see that there are 2 lone pairs of electrons on the sulfur atom. We will break these lone pairs up. Now we can bring in our other fluorine atoms. We can make bonds. We have our 2 axial fluorines. And we have 4 equatorial fluorines. In this case, our electron geometry and molecular geometries are the same. If we look at this, we can envision somewhat of a pyramid on the top and a pyramid on the bottom. Now, we've seen with PCl5 that the geometry with a pyramid on top and pyramid on the bottom is called bipyramid. So with PCl5, we had a trigonal bipyramid. In this case, we are not going to use that same nomenclature. We are not going to call it a bipyramid. What we're going to say is that this is an octahedron. If we looked at our structure, we'd realize there are 8 faces to the structure. There are 4 faces on the top and 4 faces on the bottom. And this should somewhat match our nomenclature we used with methane when we called that a tetrahedron. Is there necessarily perfect consistency in the nomenclature? No. But the people that came up with the geometries got to name the geometries, and so in this case we shall say there are 8 faces to this geometry, and it is an octahedron. Now again, if we look at the shape that the electrons make, we realize the shape is an octahedron. So we shall say that the electron geometry is an octahedron. Our species in this case was SF6. And as we look at this, we realize, well, our sulfur atom needs 1, 2, 3, 4, 5, 6 hybrid orbitals. Sulfur, again, is not a period 2 element, it is a period 3 element. So when it hybridizes orbitals, it is not hybridizing orbitals from the second shell, it is hybridizing orbitals from the third shell. So it will hybridize the single 3s orbital, it'll hybridize the 3p orbitals. That gets us 4 orbitals total. We need 2 more orbitals, and so it will hybridize 2 of the d orbitals. So as we look at the sulfur atom, we say that the sulfur atom is sp3d2 hybridized. So if an atom has an octahedron for its electron geometry, then that atom is sp3d2 D2 for its hybridization. This is important to know. Again, there is a direct correlation between the hybridization and the electron geometry. Now we turn around and say, okay, that sounds great. What does it get us? One of the interesting things of biology is how organisms are able to recognize certain molecules. And I go to nutrition and the things we eat in this consideration. If we eat something as simple as an apple, we should realize that that apple has tens of thousands of different chemicals in it. And so your body, once you've consumed an apple, has to say, well, how do I take this vitamin C, the ascorbic acid, and send it to where it needs to go in the body? How do I take this fructose and send it to where it needs to go in the body? How do I take this starch and send it where it needs to go in the body? There are, of course, things that cause coloration in the skin. Your body may take some of those and say, oh, dispose of some of those, but no, those are unique, we'll keep those. There are different chemicals that are perhaps inside the seed or the stem. How does your body know how to recognize these different compounds and send them where they need to go in your body? Some of them are toxins that your body will process and get rid of them. Some of the chemicals are needed, such as the vitamin C and the starch. One of the keys for your body to recognize what the different compounds are is shape. And we're looking at this and we're saying, well, we're recognizing the shape of the electrons around an atom. So as you're studying the geometry of an atom, you should be realizing that this is now your insight into biochemistry. We are starting your studies to get you to understand, okay, how does an organism recognize different compounds as to what it does? How does the organism recognize self from something else? So as we look at this, we should say, well, that actually becomes extremely important. If biochemical systems, organisms, are able to recognize different chemicals based off of shape, we must have some way to ascertain the shape of a molecule, and we are now in our studies on doing so. So it is important to be able to go back and forth from electron geometry to hybridization and hybridization to electron geometry. Let's go ahead and work a few examples. Let's start off with an example we've seen before, carbonic acid. We'll place the carbon atom in the middle. We'll bring in an oxygen atom. We'll bring in an oxygen atom. And we'll bring in another oxygen atom. We'll bring in a hydrogen atom and another hydrogen atom. We'll make bonds. We see an unpaired electron and an unpaired electron. We move them to the middle. We make a double bond. We redraw our structure, paying attention to Vesper. We then obtain a proper geometry for our molecule. As we look at this, we realize that this carbon atom has a trigonal planar geometry. The bonds between the electrons are all 120 degrees. So this carbon atom has a trigonal plane for its electron geometry and is therefore sp2 hybridized. We look at the oxygen atom, and we have two oxygen atoms that are equivalent. And we say, well, indeed, it has a bent molecular geometry, but we are interested in the electron geometry. And as we look at the electron geometry, we see 1, 2, 3, 4 pairs of electrons. So the electron geometry in this case is tetrahedron. So the hybridization of the oxygen atom is sp3. As we look at this oxygen atom, we see that the electron geometry is also a trigonal plane. This must be because the bond angles between the electrons are 120 degrees. And so the hybridization of the oxygen atom is also sp2. Let's consider bicarbonate. The formula for bicarbonate is HCO3 minus. You should be looking at this and saying, well, isn't this the same thing as carbonic acid, except that we took away a hydrogen and added a negative charge? And you'd be absolutely correct in that analysis. So we shall say that we have our carbon atom with our 4 valence electrons. Again, we will bring in 3 oxygen atoms. And we will bring in a single hydrogen. We will make bonds. And we see that we have an unpaired here, here, and here. We'll make a double bond between this carbon and that oxygen using this electron and that electron. And we're seemingly left with this unpaired electron. And of course, when we're drawing Lewis structures, we do not want to have unpaired electrons. But remember, the formula for HCO3 minus includes this minus. The extra charge means that there is an extra electron that must be placed on our Lewis structure. We have an unpaired electron. That electron is residing in an orbital, and we can get 2 electrons in an orbital. So we will take the extra electron indicated by the charge in the formula and pair it up with that unpaired electron. Now, bear in mind when we do so, we're placing that extra electron into an orbital, and lone pairs of electrons go into hybrid orbitals. So we place our extra electron here, and we need to keep an accounting of where we put that extra electron. We put the extra electron on this oxygen atom, and we will indicate so by placing a minus next to that oxygen atom. We redraw our structure paying attention to Vesper. Again, we look at the carbon atom here. We realize that it has a trigonal planar electron geometry. And therefore it is sp2 hybridized. We see the same thing with this oxygen atom here. We look at this oxygen atom and we see that it has 1, 2, 3, 4 hybrid orbitals. And so this is a tetrahedron. And therefore it is sp3 hybridized. We look at the oxygen atom here, and it has 1, 2, 3, 4 pairs of electrons. Each pair of electrons goes into a hybrid orbital, so this oxygen atom also has a tetrahedron for its electron geometry and is also sp3 hybridized. Let's go ahead and look at carbonate. So we looked at carbonic acid, H2CO3. We looked at bicarbonate, HCO3 minus. Now let's look at carbonate. The formula for carbonate is CO3 2 minus. We will place our carbon atom with its 4 valence electrons, and we will bring in the 3 oxygen atoms. We'll make bonds. We see we have an unpaired on the carbon and an unpaired on the oxygen. We will make a double bond. We have an unpaired on this oxygen and an unpaired on this oxygen. Again, we should not have unpaired electrons on our Lewis structure, so we will add the 2 extra electrons on the oxygen atoms to make electron pairs. We will indicate that we added the extra electrons to each oxygen atom by placing a minus next to the oxygen atom. We look at Vesper and we adjust our structure based off of Vesper. So again, our carbon atom has a trigonal planar electron geometry and is sp2 hybridized. Same with the oxygen atom. These oxygen atoms have 1, 2, 3, 4 pairs of electrons, and they are sp3 hybridized with a tetrahedron for the electron geometry. As we look at these structures, we get into the concept of formal charge. Formal charge means that we are keeping an accounting of the electrons in our Lewis structure. Now, we should be saying, all right, well, if I have a carbon atom and it has 6 protons and 6 electrons, is there any charge? No. In that case, the positive charges equal the negative charges. So formal charge does not necessarily represent the electronic state of an atom. Formal charge, again, is just an accounting where we say, okay, on that particular atom, how many electrons am I saying are on that atom in my Lewis structure as compared to the number of protons? So let's go back to our bicarbonate and look at the concept of formal charge. Our formula for formal charge is the valence electrons, so I will put VE for valence electrons, minus the bonding electrons, minus the non-bonding electrons. Let's see what we mean. We'll look over here at this oxygen atom and we will consider its formal charge. So on this oxygen atom, we know that oxygen has 6 valence electrons. Let's look at the bonding electrons. Now there are 1, 2, 3, 4 bonding electrons around this oxygen atom. But of those 4, how many does oxygen own? Well, oxygen owns this bonding electron and it owns that bonding electron. Again, these 2 electrons that came from the carbon atom are in oxygen's orbitals, but we are computing formal charge, and we are only concerned with the electrons that are actually around the atom. So although the oxygen atom has these 2 electrons from carbon in its orbital, we are only concerned with the electrons that oxygen brought to those bonds. So we shall say that oxygen has 2 bonding electrons. Then we see that we have 1, 2, 3, 4 non-bonding electrons. And of course, this gets us to 0. And when we made our Lewis structure, we did not indicate any formal charge on that oxygen atom, so our computation of formal charge matches what we determined on our Lewis structure. Let's go ahead and look at this carbon atom. Carbon has 4 valence electrons. We see that this carbon owns 1 electron in this bond, it owns 1 electron in this bond, and it owns 2 electrons in this double bond. So we have 1, 2, 3, 4 bonding electrons. There are no lone pairs or non-bonding electrons. And so the formal charge on the carbon atom is 0, which matches what we have on our structure. Let's look at the formal charge on this oxygen atom. Again, we know that oxygen has 6 valence electrons. In this bond, oxygen owns 1 of these electrons. So it has 1 bonding electron. And then we see oxygen has 1, 2, 3, 4, 5, 6 non-bonding electrons. And so our formal charge works out to be -1, which matches what we had on our Lewis structure. So formal charge should match the Lewis structure. When making the Lewis structure, you must add an extra electron if it's indicated in the formula. Once we get done making our Lewis structure, we can see where that formal charge is. When we get to carbonate, we can see that there are 3 oxygen atoms, 1 has a double bond, and 2 have charge. But is this the only way to have drawn the Lewis structure? If I think carefully, I could say, well, no, I could have drawn the Lewis structure with a negative charge here and a double bond here. And another negative charge here. I could have also drawn the Lewis structure with a double bond here, a negative charge here, and a negative charge here. If we have a Lewis structure wherein we have multiple atoms that can share charge, then these Lewis structures indicate resonance. In our case of carbonate, we have 2 extra electrons, or 2 extra negative charges. We have 3 oxygen atoms. The 3 oxygen atoms are equivalent. What we're saying is the 2 extra negative charges are distributed amongst these 3 oxygen atoms. We can think of the electrons as jumping from one oxygen atom to the other. So we can certainly draw a Lewis structure where we say, well, this charge is on this oxygen atom, this charge is on this oxygen atom, and the other oxygen atom has a double bond, and say, well, on this Lewis structure, I'm drawing them as fixed. Bear in mind, in reality, these electrons are moving amongst these 3 oxygen atoms, and we call this movement resonance. It is important to be able to draw Lewis structures. It is important to recognize that the resonance structure will indicate the hybridization of atoms in that Lewis structure. Bear in mind, if we have multiple atoms, we've seen carbon and oxygen, that there are atoms within this Lewis structure that have multiple hybridizations. It's also important to be able to ascertain the electron geometry as well as the molecular geometry of the atoms that are in the Lewis structure. You will need these skills in your further chemical studies.